And the first talk of three really interesting talks is by Akshay Gopalakrishnan from McGill. He's a PhD student there.
Good morning. This is Akshay, and I'm going to talk something about memory consistency models and its interaction with program transformations. So what is this about? It's about shared memory concurrency semantics, which talk about memory visibility guarantees in hardware, and it's also extension in programming languages. Specifically, we are talking about correlation with optimizations, or rather program transformations, as we call it. And we try to answer this question of whether we can formally describe a concurrency model as a set of these optimizations. So we shed some light on this in this paper. So let's just start with the most simple memory model, which is sequential interleaving, also known as sequential consistency. You can think of it as each processor reads directly from the main memory itself, so there's no buffers or caches in the middle. So if we use this kind of sequential interleaving, let's take an example where we have two threads, X and Y, represent shared memory. A and B are local to T1, T2, and T1 does a write to X, followed by it reads from Y, and T2 does write to Y, followed by read to X. So one simple sequential interleaving outcome is A returns as 1 and B returns as 0. And this is possible if both memory accesses of T1 are done first, followed by T2. So that's a simple sequential interleaving. And you can think of the other variations of interleavings possible. The other case is something which is not a sequential interleaving, which is where both A and B return 0. And this is because if I want A to return 0, it must be before X equals 1 takes place. And similar for B equals Y, it should be before Y equals 1. And you can clearly see there's no sequential interleaving. There's actually some form of cycle here. And this example is called store buffering. I'll tell you later why it is called so. So such strong memory visibility guarantees, that is, every CPU reads directly from the main memory, it actually affects performance. And therefore, hardware today drift away from such strong guarantees using various kind of read-write buffers, sometimes speculation, and then caches, etc. Thus, we have weaker models that drift away from sequential reasoning to talk about programs and how they behave. And so one such example is total store order, where each CPU has a FIFO write buffer. So every write issued by a CPU is first just given to the write buffer, and it can continue doing later reads or writes. So reads will first see if there's any update already in the buffer, it'll read from there or directly from main memory. So if you look at the same program under TSO, it's actually a store buffering outcome, which is A as 0 and B as 0. And why is that? Because if CPU 0 runs T1 and CPU 1 runs T2, then they can just buffer their writes, and the subsequent reads can be taken from main memory because there is no update in the respective buffers for Y and X. So what do we know from this and weak memory models? We have this kind of picture when it comes to concurrent behaviors. So SC has, let's say, this red circle, and then TSO has more behaviors, strictly more behaviors, and then the outer rings are variations of like ARM, and the bigger circle is of C11 Java and other memory models. So to answer our main question, whether we can formalize models as a set of program transformations, we asked first, how does it look for a set of program transformations? Let's take SC and TSO. How does it look? Well, before that, we'll have to connect. How does what we discussed so far relate to program transformations? Well, if you look at the same example again, we can note that if we do write-read reordering, let's say of T1, So T1s to axis Cs are reordered. This outcome, the store buffering outcome, can then be justified by sequential interleaving. So if you look at it, let's say, so B equals Y, if T1 is done, and T2's Y equals 1, A equals X is done, and T1's X equals 1. So in some sense, we get this store buffering behavior by just simple right-read reordering. Now, what does this tell us? It tells us right-read reordering is unsound under SC. But also from previous work, we know that it's right-read reordering is also sound under TSO. So for all programs, we can do right-read reordering under TSO model. So we asked, okay, what about other sound transformations under SC? Do we get all transformations under SC free in TSO? Well, the initial intuition is, why are transformations unsound? Because they allow for more concurrent behaviors. And so intuitively, it should be that weaker models allow strictly for more sound optimizations. But is that the case? Well, we looked at thread inlining, which is another sound transformation under SC. And long story short, what this inlining does is it merges the code of two threads. So in this case, T3, T1 are merged. And why is this safe or sound under SC? If you look at this outcome, red outcome, if A returns as 1, it implies that it happens after Y equals 1. And if D is 0, it happens before Y equals 1. And same reasoning for X, B equals X and C equals X. And we notice that there's actually a cycle here. So therefore, there's no sequential interleaving that can justify this outcome. And after inlining, it's the same case. We have a cycle here, if you note. So no sequential interleaving even after the even after transformation, we don't have a sequential interleaving justifying this outcome. So why this example? Well, it actually looks a little different for TSO, under TSO. And why is that? Well, the original program itself, there's no issues. We do have this ordering between the reads, and that's because if the buffer that does Y equals 1 is flushed, it's visible to both T4 and T1. Thus, if I need D as 0 and A as 1, there must be a fixed order between the reads that's happening in an execution. And similar for X, and therefore we have a cycle. So you can think of it intuitively as T1 and T4 don't use their write buffers. So you can think of it as an SC execution. So there's a cycle instead of a sequential interleaving. But if we inline it, then the visibility of this update to Y, to A equals Y, does not necessarily mean that D equals Y must be done before. And this is because A equals Y can read that value directly from the write buffer. So in some sense, this outcome is actually allowed in the transform program. So similar to what we saw of store buffering, where it allowed the store buffering outcome under SC, now it allows this outcome under TSO, which means although this transformation is sound under SC, it's actually unsound under TSO. So what do? Is it actually a disjoint set of transformations? Not exactly. It's actually an intersection, and there's another transformation, read after write elimination, which is known to be sound under both. So we have this kind of picture with respect to set of program transformations, at least for SC-TSO. But we really want something which is nice, like the Venn diagram of weak memory behaviors. So you want something that contains SC. We want a set like that. So we asked ourselves, can we build and describe such models? Specifically, if I give you SC and I give you an optimization or transformation that's unsound, can I get a model which gives me that beautiful Venn diagram? And so for this, we actually start off with an axiomatic model of SC. Briefly, what's an axiomatic model? It's a bunch of rules that apply on executions of programs. And if the rules hold for a given execution, that's consistent. Or in terms of SC, it is going to be a sequential interleaving. So what kind of axioms do we use? Well, we use axioms which are of this form. Don't be too scared of these diagrams, but PO is simply syntactic order. RF is, let's say, B equals 1, then that means it's coming from X equals 1, so we have this edge. So our programs or program executions are viewed as these graphs, and our axioms are like of this form, where let's say PO and RF edges together should not have any cycles. So if this is our memory model, then this is inconsistent under such a memory model, and this is a consistent execution. So we use such axiomatic models. And why do we use such axiomatic models? Well, we noted that the reason a transformation is unsound, as if we see in the previous examples, it's because some axiom for a given execution of the original program is violated. Some axiom is violated. But in the transform program, for the same execution, the axiom is not violated anymore. And that's why the transformation becomes unsound. So we thought, okay, why don't we just remove the axiom? Is it possible to just remove the axiom such that we get the model? But yeah, we have to be careful. We have to remove the axiom such that we can also ensure all other optimizations, let's say SC, are transferred. So we attempted to do this. And what we need to prove, we identified there are 3 things to prove. One thing is, first of all, the transformation we want that's actually allowed in the transform model, which is sound. And for the beautiful Venn diagram, it allows all the transformations in the original model, which we define as complete. And the third part is something of future work, because if we want to allow a specific transformation, we shouldn't remove more axioms than required. So we should be careful about this. And this is something we are keeping as future work. So what's our trial? Well, we use SC, and we allow reordering of independent reads. And okay, so this example is showing why it's unsound under SC. So simply, in this program, if you just look at it, if A is returned as 1, by sequential reasoning, we also know Y should be viewed as 2. So B cannot be 0. But if you reorder the 2 reads, as in this case, there's a simple sequential interleaving justifying this outcome. So therefore, it's unsound. So, okay, sure. So what kind of axiomatic model do we use? Well, we use an axiomatic model which looks like this. It has 5 axioms. Actually, there's a 6th one, which involves read, modify, writes. But as of now, we don't incorporate read, modify, writes. So these are the 5 axioms, and we identified the axiom which causes our problem, makes it unsound. And specifically, it's flavor of this. You can read the paper to understand more about this and these definitions. The point is to show that this is the process of deriving an axiomatic model. So soundness was easy because we identified the axiom that's problematic, we just removed it, done. So soundness was easy to prove. But how do we prove completeness? Where do we start? We don't have a set of transformations. How do we define this set? We have no idea. So if you look at this example, this is technically a transformation. It is a syntactic change, except yours. You're just doing all sorts of mix-match here. So okay, so the major part of the paper is defining what a transformation is, and and then we realized, okay, we can prove completeness, but for a significant set, not the entire set. So for transformations that preserve read-to-write syntactic order, we have SCRR complete with respect to SC. So it is possible, and in some way it is possible to define the set by negating or restricting transformations. And what's the point of all this? We thought about it. It was first a theoretical question. Now we're like, what is the point? Well, if I have SC, and I have some programming language model M, And tomorrow I come up with a complicated optimization, and I'm like, hey, I can prove it sound for SC quite easily. I have to prove it separately for all the programming language models. And I'm like, oh my God, this is going to take a long time. But if I have some information about completeness, it makes my life very easy. And so there we go. So this is the kind of work we are doing right now, and this is the summary. Memory models are not compositional, may not be. We propose a way, and we also found a way to describe set of transformations. And this is some future work. I can discuss it later offline, and thank you for your patience.
So at least for the motivation, it seemed like you were focused on hardware memory models.
Yep.
In a compiler, it would often be with respect to a language
Yes.
model. How could you say how that affects things, or what is your main target?
So traditionally, when we design memory models, it's mainly for hardware. And so when we go towards programming language level, we cater to C first, that can it be compiled to different hardwares as efficiently as possible? And then later we look at, optimizations. Are they sound or not? So in some sense, the hardware model itself, the memory model is designed in some sense like I add these hardware optimizations, and this is my model. So that's why I'm getting the beautiful figure of the weak memory behaviors. But I don't have such a beautiful figure for optimizations. So we want to propose an alternative way of building such models for programming languages and try to see how it interrelates to each other. So yeah.
Thanks. So you started with SC and you added the reordering, right?
Yes.
Could we start from TSO and add the inline?
Yeah, we could do that.
What model would you get?
What model would we get? I would say it's just SC plus SC plus write read reordering. That's the intended one. So we should ideally get that. But we still have to show for completeness and optimality. I think optimality, TSO, I think your work showed in some sense it is optimal. But for completeness, it's still a question mark. So.
Last quick question. All right, thanks, Akshay.
Thank you.